So I'm Paul Gazzillo. I'm an assistant professor in the computer science department. I've been at UCF since 2018. Before that, I did a postdoc for 2 years at Yale and Stevens. I graduated from NYU before that, my Ph.D. So my main research interests are in programming languages and program analysis, and in particular, how they can be applied to software engineering and software security. In terms of accolades, this year I got the Career Award, and within my own community, the program managers community, I've gotten a research highlight several years ago. So these are my students in my lab. So I've got 2 PhD students right now. One is a visiting student, one is a student at UCF, and a whole bunch of undergrads, and they're fairly evenly divided between 2 projects. So to give a little background on my interest, my main focus is really in the security and reliability of software. And the reason for this is probably pretty obvious. Software is becoming more and more ingrained in our everyday lives and everything that we do. So breaches like the Equifax breach, which revealed millions of people's personal information, was due to a really minor software bug that lived in the code base for some 10 years. And attackers have been moving towards more sophisticated attacks like Sidechannel Attacks, which I'll talk about in a little bit. Meltdown Inspector kind of blew up the internet. They were vulnerabilities in basically all modern Intel and AMD processors. And even more importantly, all of our devices are being equipped with these internet-enabled chips. So Jeeps, medical devices, cars, guns, refrigerators, they're all becoming software components. And so this security researcher, Bruce Schneier, puts this really eloquently. As everything turns into a computer, computer security becomes everything security. And so there's a bunch of approaches that we can do to try to deal with this. There's antivirus tools and firewalls. The problems with these is that they're kind of reactive. They have to be constantly updated with new kinds of attacks. And so one of the standards for security critical software is manual code review. So software is written by humans, and if you can sit down and really carefully check to make sure that your software is safe and secure. But I'm a computer scientist, so my view is, can we automate this process of auditing software and making software safe and do it automatically? And program analyses, and this is called program analysis. So program analysis has had some really great success over the past couple of decades in rooting out software bugs. Because software bugs have historically been the root cause of so many security vulnerabilities. But as they get repaired, I've been looking at sort of non-traditional applications of program analysis in 2 main areas. One is configurable software, which I'll talk about in more detail. And here I've been the most active. I have several publications, a couple of active grants, and about half of my students are on this. And the other side is Sidechannel Attacks. And this is a kind of emerging threat that's not just theoretical anymore, it's being exploited actively by attackers. So let's look at this configurable software. So configurable software comes from the fact that when developers make new devices, if they make a new car and they want it to be internet enabled, or they make a new refrigerator and they want it to be internet enabled, they don't sit down and rewrite their entire software stack. Instead, they use some open source or existing software and repurpose it to their application. So that's why you see 70% of IoT developers, Internet of Things developers, using Linux. Your car may now be running a Linux device. And the reason for this is that Linux and other software like it are highly configurable. They can be customized automatically by selecting configuration options, and all this can happen without actually reprogramming the software. And this enables extreme reuse. That's why you see a similar software stack used in data centers and mobile phones and cars. A lot of the same software is used because of this extreme configurability. And there are billions and billions of these devices running a lot of the same customized software. The problem is that this configurability is a massive headache for program analysis and a massive headache for security and reliability. And the reason for this is that our traditional automated tools that can do a really good job of checking the safety of software, they work on one of this variation of the software at a time. But because of this extreme configurability, there are literally trillions and trillions of variations of the software. And it's just not feasible to check all of these one at a time. Moreover, this kind of software, when developers build in this configurability, it actually makes, studies show that it actually makes the software buggier and harder to fix. And so in short, a little overview of what this looks like is you have this giant code base. So if you take the Linux kernel, it's 20 million lines of code, and it gets run through this automated configuration system to take a slice of the code. And that little slice is what gets installed into our cars and refrigerators. And traditional program analysis tools work on that subset of the original software, that slice. And my main goal is to look at the original source code and the full code base and analyze it, all of it simultaneously. So there's a lot of research challenges with doing this. And so, basically all of the tooling that goes into constructing this software needs automated support from tooling. And so a lot of my past work has been providing this support. So looking at the build system, looking at the front-end analysis of the language, allowing bug finding to work and security analyses to work across all of these configurations of the software. And some of the future work, particularly in the career grant, is trying to formalize this notion of software configuration. Historically, it's been it's documented in human language, but it hasn't been automatable. And so part of my research effort has been to kind of formalize this notion of software configurations so that ultimately we can automatically prevent this kind of misconfiguration problems that emerge in this configurable software. Okay, so that's the analysis of configurable software. Let's look at sidechannel attack mitigation. So if you haven't heard of sidechannel attacks, the way they work is they leak secrets indirectly to attackers. So software that we rely on for keeping our passwords and keys and other private data safe, historically, attackers have been able to steal this information by exploiting bugs in the software. But as software development has become more sophisticated and more and safer, attackers have been turning more towards these sidechannel leaks. And the reason is that they can leak secrets from software, even if the software is completely correctly written, even if there are no bugs to exploit, and the attacker doesn't even need to break into a software system or a computing system in order to steal these secrets. And that's because secret information is correlated to runtime performance of the device, and attackers can infer what secrets are being processed. So to see a little diagram of how this works, at the top we have some computing device that's running encryption. You take your secret key, you take your plain text, you run it through this encryption algorithm, and you get your confidential output from that. So theoretically, nobody can reverse that process or read it. But an attacker, without breaking into a machine, can observe this encryption running, and just by watching power consumption or timing information, they can actually infer what the secret key is used to run this encryption algorithm without having to exploit the software by breaking in. And so the current solutions require a lot of expertise in analyzing these kinds of attacks and really just redesigning and re-implementing vulnerable software. So as you can imagine, only the most sensitive software gets this kind of treatment, gets this special treatment. And so automating this process has been really hard. So what I worked on in my postdoc is a team trying to detect the potential for these kinds of attacks. But even if we can detect it, it still requires hand rewriting the software. And so in collaboration with Dr. Jan Solihan and Dr. Gary Levins, who are in computer science and the cybersecurity cluster, we're looking to automatically remove these kinds of, prevent these kinds of vulnerabilities from software. And the problem is really tricky because the vulnerabilities occur because of both hardware and software properties. And so our goal is to have this hardware-software co-design where we introduce new techniques in the programming language and new techniques in the hardware to work together to remove these vulnerabilities, these sidechannel vulnerabilities. So in conclusion, my main research effort is novel program analyses for future security problems. The active areas that I'm working in now are this configurable software, this problem of configurable software, and sidechannel attack mitigation. And so because I'm just in general interested in software security and reliability, some opportunities for collaboration are any companies that are doing software development heavy work, and also industrial and civil engineering researchers who are working on smart devices. Anyone who's trying to integrate software into their physical devices. I think there's a lot of interesting problems for us to work on there. So thank you, and I'll take whatever questions you have.